My name is Julius, and for today's talk, I'll talk about software engineering analytics. So here's how we can go about it. First, what we'll do is we'll talk a little bit about the science behind why we want to do analytics and how you can actually use it when you lead a team, for example, or you can even share it with your boss or with your team members. So we'll talk a little bit about the sciences behind why we need to do it and some practical applications using Google Cloud. But of course, you can use other solutions as well if you wanted to. So here's the problem that we face actually. As a startup, we started off with just about a bunch of people, trying to figure out how we go around with our solutions. But then as years go by, the startup became more and more successful, and we actually reached a point whereby the number of engineers in our team grew from somewhere around 5, 10 to actually about 25, 30. And so once you grow to that number of engineers in your team, what's going to happen is that it becomes more and more difficult for you to see who's doing what, how are they performing, and try to figure out who to best reward. Moreover, because you have so many engineers already, right, it becomes more difficult for you to also know what kind of progression, what kind of plan can you do for your engineers to become better at doing what they're doing. It becomes more difficult to mentor people. And so now, instead of doing a one-on-one mentoring and trying to figure out how you can best improve their career, now we have to see how we can mentor at scale. So this is one thing why we want to do a form of engineering analytics, which for sure Google has been doing for a very, very long time. So the good thing is that we have a lot of data. In fact, every time we commit code to Git, there's data to be used there in order to improve the quality of our code and the practices that we are doing as engineers and also as a company. As a CTO, some of the things that I think about, right, always has to do with how can I maximize productivity. Of course, one way to see it is to kind of squeeze people and make them perform more and more. But another way to see it is to think about how you can balance employee happiness, engineering efficacy, and consider how they can continue to be as productive as they can be and as happy as they can be in the company. Why is this important? Because our research shows that if your team is engaged, if they're very happy with what they're doing and they want to continue to contribute to your company and to the business, they can outperform their competitors by as much as 147% of productivity. Just to be clear, this is not 14.7%, this is 147%. This is doubling your headcount and more. And that you don't have to double the size of people and risk communication challenges. All you have to do is to make people happy and engaged in your company. So here's some of the ways that you can do that. There was a research by Microsoft, and this was published in Wharton School of Business. And what they found is that there's a certain amount of overtime that's productive for your company. And the moment you hit that threshold, suddenly the engagement drops by a lot. And so how did they find this out is that they surveyed different team members in different teams in Microsoft, and they found that so long as people spend less than 44 hours at work or less, they're fine. They're happy. They can produce a lot of value. But the moment they go beyond 44, the engagement drops. So it's very important then for us as a company to track over a period of many months or even years how much time does the engineer spend inside of work and outside of work. So how we are able to do this is that we are trying to see when they are committing their code. So sometimes you will commit your code within work hours, but sometimes there are situations where you're actually going to commit your code outside of work hours because those are the time that you're still productively working. Of course, this is not 100% accurate, but it gives you some form of indication whether it's going up or not in terms of overtime work. So here's an example. This is a real data, by the way, where we have found that over a period of 2 years, engineers are spending somewhere between 5% overtime to 15% overtime. The moment we reach 20%, it will be a danger zone for our company. So it's a very good means for me to go to our HR, our CFO, and our CEO to say, hey, we need more resource, right? Either we need more engineers or you have to limit the amount of work coming into the engineers so that we can sustain this kind of workload. So without data, it becomes very difficult for us to go to the executive team and say, hey, something is wrong and we have to fix it. With data, it becomes more and more easy. Here's another thing that I think about. So, when somebody leaves the company, they carry a lot of domain knowledge with them. In the same way, when you join the company, during the interview, it looks so good, and then you join the company, and then you realize the code has some problems, right? This happens to us. This is normal as an engineer. One thing that you have to do is to try to also prevent knowledge decay. In the software engineering lingo, we call it the bus factor, right? Which is the number of engineers that has to be hit by a bus before the project collapses. That's how we we are unique as engineers, I guess. So here's another example that we can do. So in a company, you have different types of projects, right? You may have your Android project, you may have your backend projects, front-end projects, and each of these projects, you have contributors, right? You have employees in your company who commits their code, and it's very important then for us to try to find out who are the most productive contributors to each of these projects. Because if we are able to find out who are the productive contributors, we are also able to find out the knowledge gap between these contributors. So here's one example. If you look at John, Cheryl, and Sandy, the first example, you can see that the amount of difference between the three of them is not too much. So even if, let's say, for example, John leaves the company, Cheryl and Sandy are still able to sandbag the damages caused by John's departure. So that project is safe. But then if you look at project number 4, you can see that Dawson has a significant amount of knowledge difference compared to Pradeep and Vishal, which then means that if Dawson decides to move on, then it becomes very difficult for Pradeep and Vishal to catch up. Then if I am able to see this, I'm able to basically go to Dawson and say, hey, are you able to actually distribute your work to your 2 team members so that we can distribute the knowledge so that we can sandbag any danger that might happen if somebody leaves, for example, Dawson. But then you have project number 5, the one at the bottom, where Enrique and Carl has already left the company and the whole project is being held together by Pragati, which then also means that if Pragati goes on leave, if she's sick, if she moves on, then the project will have nobody else to take over. So that one is very, very dangerous for the company, right? Which then means that I can, if I'm able to see this, I'm able to say, maybe go to project 2, project 3, even project 1 to say, hey, maybe you can move to this project. Or that would be an indicator for me also to speed up hiring for that project. So how we are able to find out the most productive contributor is to just try to find out who are the most productive people who's committing code in that particular project. Again, it's not a 100% accurate indicator, but it kind of gives you a sense of like who's the most productive there. This is monitoring at scale, and it helps you make decisions better as a CTO. Here's another one. Another thing that I think about is how can I know the velocity of my team? How fast are we delivering, and how can we do better? As with everyone, we want to do a good job, and in order for us to do a good job, you also need to measure how we are performing as a team. So normally, what happens is that you will commit your code, and somewhere after you commit your code, there will be a pull request. So somebody will review your code, and then it gets merged. And then once it gets merged, you deploy your code to production. So you have these 3 stages of moving your code from the first time you committed to actually your code reaching production. So it's important for us to monitor this as well, because there are times where there will be a bottleneck that's very difficult to figure out. You will hear people complaining about things here and there, slowing down here and there, but it's hard to actually pinpoint unless you have data to monitor it. So how can you monitor it? Well, it turns out that when you use Git, you can actually pull out data from when people first commit for a particular release, when the pull requests are made, when those pull requests are merged, and when that merge goes to production. So for this example, you can see that although the blue part, which is the first commit to a pull request, it doesn't move so much, right? But then when you look at the yellow portion, the part where the PR to merge, the pull request to merging it to your proper branch, in this case perhaps master or develop, it actually increases over time. So it gives me a sense that, hey, maybe something is wrong here. Maybe the one who's reviewing the code is overwhelmed. Maybe the one reviewing the code is new. maybe he's burnt out. There's all sorts of reasons that this could happen, and you can only find it out when you have objective data at scale. So here's one way to actually solve that problem. When you connect your Git repository, pull the data, and put it to some form of data warehouse that you can make an analysis later. Here's another one. How do we reduce defect density? It's also very normal for us engineers to actually want to create quality product, quality code. But then sometimes it gets difficult, right? Sometimes when you have to work with complex features, then the quality of your code goes down. So here's one way for you to be able to solve it. It turns out that there was a research, this was done by Cisco and SmartBear, where they found that the magic number in terms of lines of code per commit is somewhere around 200 to 250 lines of code. And what they found is that the moment you hit 200 to 250 and beyond it, the reviewer will actually get lazy. And it's not their fault. It's because they get overwhelmed with the amount of information that they have to process and check. So the idea there is that every time you ask your reviewer to review your code, it has to be somewhere between 200 to 250 lines of code. But of course, less is also better. So then how do we coach our engineers to do it? One way that we did it was to actually create a dashboard for everyone to see. And then of course during one-on-ones, the engineering managers can talk to their staff to see that, hey, maybe somebody else is performing better than you, and here's perhaps how you can do it. So in this data, it looks a bit small though, but you can see that there are green boxes and red boxes. And how this works is that over week, we are displaying the average lines of code per commit. And what we are trying to show here is that the moment you reach above 250, the box goes from green all the way to red. So then it's very easy for me to say, for example, if you see the third column here, Bella might need a bit of help in terms of the lines of code that she commits. But you can see, for example, that Anthony, the one on the second line, seems to be doing just fine. So there's a way for us to also indicate that maybe you could do a bit better in terms of the lines of code that you put in your commits. Google also published this very interesting research. In fact, it wasn't really Google. It was an organization that Google eventually acquired. It's called Dora. And what they do is that they go around small companies, big companies, and they try to figure out what kind of indicators that these companies have that predicts a very productive engineering culture. And what they found is that it doesn't matter whether your company is small or big, as long as these properties apply, it makes it's a good indicator that the software engineering culture there is very good. And here are the four. They found out that if you deploy on demand, it means that every time you want to deploy your code, you can just go ahead and do it. It's an indicator that your culture is very, very good and you're a high-performing culture. Whenever the lead time for change, which is the amount of time it takes for your first commit to reach production, the lower the amount of time it is, the better your organization is. Which then means that waterfall could be a bit questionable in certain aspects. There's also time to restore service. Once in a while, our services will fail. There will be issues in production. And they also try to measure how long does it take for you to fix production issues. So if you're able to fix it in less than an hour, then it means that you're a high-performing organization. Finally, there's a change failure rate. So they try to find out as well, the moment something fails, right, how many successful deployments did you have for one failure to occur? So of course, the lesser failure, the better. So what they found is that the magic number is somewhere from 0% to 15%. So I actually had to put 20% there, but it should be 0 to 15. So those are the numbers, which then means that as a company, you can actually track all of these as well with the information you have in Git. So here's how we did it. First, let's talk about the change failure rate, the rate of failure for every successful production release. So here's how you do it. Has anyone heard of semantic versioning? Semantic versioning is like when you name your releases as 1.0.0, 2.1.1, that kind of thing. So when you do semantic versioning, how we did it was the moment the number that ends, the last number, the moment it's a 0, it means that it's a release. It's a proper release that's not a hot fix. But then if it ends in a non-zero number, it means it's a hot fix. So what we are trying to do is to try to find out all the releases over a period of time, how many zeros are there and how many non-zeros are there, and we divide it. And that's how we derive the change failure rate. So how we are displaying it then is that we are showing this to our product managers, our CEOs, our engineers. And why is this important? Because change failure rate increases when the amount of product work increases. Because it overwhelms engineers when there's too much requirement for them to do, because now they have to come up with more features, more work with the same manpower. So then we can actually show it to the product manager and say, hey, we have to slow down a bit in terms of our the inflow of product requirements so that the engineers can catch up. Then without this, right, it becomes very difficult for us to negotiate with our product managers, with their CEOs, why the engineers are not producing the kind of quality that they ought to produce. Here's another one, mean time to resolve. This is quite important as well. Mean time to resolve, again, as I mentioned, is the amount of time it takes for you to resolve production issues. So how we are able to monitor this is to see the data, the time difference between when a non-zero release is created versus a zero release. So with that average, we are able to see how much time does it take for us to recover from a failure. So we display this for our backend team, for our front-end team, for our mobile team as well. We have a change lead time as well. And for our company, we actually do a weekly release. So because we do a weekly release, right, a change lead time should be 7 days, including weekends. So all we have to do is to try to find out the difference between two releases, the amount of time it takes. And then as long as it's 7 days, it's fine. So that's just how we do it. So you might want to consider that as well in your company. Lastly, we do a deployment frequency monitoring as well. For us, our web team and our mobile team, they release once a week. But then for the backend team, of course, they can release on demand. So in this case as well, we also try to monitor the same. So how can we do it? So how can we build the infrastructure to make it happen? So here's how we do it. You can use all sorts of solutions that you may want. You can use competitors' product, but you can also, of course, use Google Cloud as well to make this work. So first, we are using GitLab as our, how should I say, our repository. But of course, if you're using Bitbucket, if you're using GitHub, that's fine as well. If you're using Microsoft TFS, that's fine as well. So because all of these solutions, they have APIs that you can call, which you can pull out information about how your team is working on it, how they're committing their code, the tags, the releases, so on and so forth, which you can analyze later on. So how we did it was we actually used Python, but of course you can use Java or Scala as well, or any other language that you might want to use. And what we do is that we pull information. They offer APIs. We pull information from the API, and then we dump it to our Google Cloud storage. So if you're familiar with data engineering, we use Google Cloud Storage as a data lake. Data lake is a place where you store information before you send it to your data warehouse. You want to do that in order to post-process any data that has been received. If something goes wrong, number one, and number two, also to have a track record of data that came in before it goes to your warehouse. Because the moment it goes to your warehouse, it may be processed already. So how we are doing it is that we are using Python pandas for it. Of course, if you're using other languages, that's fine as well. So once the data goes to your cloud storage, the next step is to actually pull information from cloud storage into a database. So in this scenario, there's actually multiple ways by which you can solve it. When we were working with our account manager, one of the questions that they ask us is that why don't we use a relational database? Google BigQuery is a columnar database. It's very useful for analytics, but it's not as effective when you want to process a row-based data. And also, columnar database is much more expensive. So why we use Google BigQuery is because now we are just analyzing software engineering data. But in reality, when you work in a startup, even in bigger companies, you can actually triangulate information that your software engineers are doing with what your product managers are doing, with what your project managers are doing. You can even triangulate information in Slack. Let me draw a picture that for what you can do, and then I'm not going to discuss how we can do it, but I'll draw a picture of how we can improve this. So imagine this. Many of us are using some form of project management tool, perhaps Asana, perhaps Jira, or other project management tool. These management tools, they also have APIs. There's a lot of activities that's happening there, which you can pull data from and put it in your data warehouse as well. You have Slack, for example, where you may not have access to private communication, but in public communication, the things that people talk about in general, in random, you can draw out a social graph. And you can even draw out using some of Google's machine learning APIs to try to find out what kind of sentiment are the conversations like? How's the animosity? How's the friendliness? What kind of sentiments that does the conversation evoke, and who's talking to who? You can triangulate these information and say these people are working better together than other people. So you can not only see on a grand scale of things how people are being productive, you can also drill down one step deeper and say, why is these two people more productive than these two people? Why is this person productive when he's working with that person but not this person? You can ask all those questions. So the moment you scale your data analysis that way, a row-based database will not work because you have so much data for you to process now, which BigQuery, columnar database, can actually help you do. Hence, we decided to use BigQuery because of that. Of course, it's not just this, right? You can even triangulate things like hiring, for example. When you hire people, how did your engineers evaluate the candidate? Who did they pass? Who did they fail? How do you triangulate that information during performance evaluation, right? Because sometimes you may rate a person low in hiring, but they turn out to be star employees. You may rate a person very high in the hiring process, but they turn out to be not so good employees. So you can triangulate this information as well. I say this because although we are talking about software engineering analytics using Google Cloud, you can a lot of these things into other forms of data that you can collect to improve your performance as a company. So going back, we use Google BigQuery for this particular reason, and we pull data from cloud storage and process it using Google Cloud Python API and sending it to BigQuery. Next, we can use Metabase as a means to visualize our data. You can use Google Data Studio. You can use Looker, for example, which is also by Google. And so the whole idea is that the moment the data is now in your database, the next step is, of course, to display it. And the examples that I have shown in previous slides are actually by Metabase. So in terms of our DAG, DAG is like, if you're familiar with data engineering, DAG is pretty much what data engineers are working on. But if you're not very familiar, it's actually very easy once I explain it. So DAG, the way it works is that when you want to process multiple stuff in a pipeline, some of the things that you do, right, you can do it in parallel. So in this case, for example, we start the DAG. And then we try to parallelize the APIs that we can call together that are not dependent on each other. And then because once we parallelize all of them, we might want to collate information and that comes from the next API. So we can parallelize things, and then we can also make things step by step. So we did it so that we can move things as fast as possible by running things concurrently. So you do this as a data engineer. As a backend engineer, you probably have done it quite a few number of times. So this is just how DAG works. For Google, they have Dataflow for this. But in our case, we decided to use Airflow just because we are more familiar with Airflow. You can, if you're using other services apart from Google Cloud, they have similar solutions as well. One challenge that we run into is that it turns out that when you use Git, right, you are actually given privilege by your admin to have your account associated with your GitHub repository, your GitLab repository. But it turns out that the way Git works is that even if your account is associated to your code repository, whenever you do a commit, the email and the name that's tied to it is actually just a string, which then means that we have to associate the name and the email to an actual account in your GitLab or GitHub profile. Because you can use your personal laptop to check in code, which may have a different email and name as compared to your work laptop, for example. So that's one of the challenges that we run into, but the rest are quite trivial. So these are some of the APIs that we have used, but of course you can just like go online and pull out the data if you wanted to. Because some people are taking pictures of it, I probably stole for time so that they can take pictures of it. This is, by the way, recorded, so you can also go online and see the slides as well if you miss out. And then these are more APIs that we have used. There are more. Oh, another thing is that when you use their APIs, right, especially GitLab will suddenly change their APIs without notifying. Yeah, yeah. So that could be another issue. GitHub, we haven't used GitHub before, their APIs, but they might have the same issue. So just to highlight that this could be some issue if you decide to do so. I think that's it. Thank you so much for listening. Hope that was helpful for you. I'll be happy to take questions if anyone has. Yes, sir.
What are some of the vanity metrics that you have identified? And maybe you can share with us if there is.
Vanity metrics.
Because I put just one of it for the sake of quality.
Oh. I'm not sure if we did any vanity metrics though. Although there was one graph which I didn't surface here. We tried to find out the hour of day that people commit. So we found that some engineers they work from 9 to 6. They really work from 9 to 6. As in, like after 6, right, they disappear. There are some engineers, right, who are very active between 11 p.m. to 2 a.m. I don't know why. So what happened was, because we have a table, we have basically a graph, right, of all the engineers' names and the time of day they come. So it was actually helpful for me to actually go to them and ask, like, why are you still awake? Like, what are you doing? Yeah. But apart from that, I don't really recall any. Oh, there was one actually. I'm not sure whether this is considered vanity metric or not. There was one guy who committed like more than 50,000 lines of code. Yeah, and then we were like, what just happened? So it turns out that he was trying to get rid of a particular repository, and what he did was he moved his code from one repository to another, something like that. But yeah, but I don't remember anything really interesting beyond that. I work with Shangi though, so if Shangi can remember anything, it will be interesting to know. Yeah. Well, I guess we can move to the next question first. If Shani comes back, we can ask him. Yes.
Just a general question. So the engineers from 11 p.m. to 2 a.m., the project that they were on, did the workload suffer because they're all working at different times?
Not really. So some of them they just like to work.
Yeah.
Yeah. So yeah. They're fine. So when I talk to them, right, they're like, oh, actually, at during work, right, they're the engineers who likes to coordinate with other engineers. So they have the only time they want to productively commit their code is during those wee hours. And some of them also they want to experiment on things which their actual work during the daytime doesn't allow them to do so. So they will do it during those hours. Yeah. Yes, sir. Yes, yes, boss.
How do you manage like false positive or false negative from the start? So for example, like maybe a more senior engineer might spend more time in analyze and maybe documentation or study the solution instead of like committing code. So maybe in the start, then you see that, oh, actually they are writing less code, but they are actually spending more time for investigation and stuff like that. So that might give a little bit of false positive or false negative. Then how would you like manage those?
Yeah, I think you're right. It's actually very difficult to manage false positives and false negatives because it's a data at scale. So unless we know exactly what the noises are, right, is to ask those questions. How come your code is going down, or the number of lines of code is going down? So if they are able to give us more information that, oh, it's because of this and that, it makes it helps us make better decisions. Because the flip side of it, right, is that if we are not able to ask those questions and we don't have data to show, what happens is we make assumptions. So one thing that I think it would be good for this group to know, right, is because for us engineers, we generally want to just put our heads down and do work. And we tend to not actually champion what we are doing. And the difficulty there is that if you have other engineers or other team members who are championing their work, right, it makes it easier for upper management to see what they are doing, even if we are more productive. So with this data, it helps equalize the board game. Yeah. So to go back to Jacin's question, it's very difficult to find out false positives and false negatives. But what this does is it inspires us to ask more questions. Then with that, then we can clear up those edge cases. Yes, sir.
In the semantic versioning, we also got the fix, the fix, the change factory. You also analyze those steps
For refactoring.
for the commit. We have the fix, breaking change, those steps. Do you analyze that too?
Breaking change, yeah. We don't actually. But I can highlight something that might be similar though. We don't analyze breaking changes because it's something that unless the engineering manager gives us a warning that there will be some breaking changes to impact the data, it's hard for us to know from a high level what's going on. But I can highlight something else, which is so our team, right? It's divided into different projects. What we found is that one team, right, the amount of code that they commit is very, very low. And then other teams are just roughly the same. So it inspired us to ask a question: why are you not committing enough code? And these other your other team members, right? They're doing so well. And it turns out that it was because the code base is such a mess. So it takes so much time for them to actually read and figure out what's going on. So perhaps if we see a dip also, when you see a dip in terms of productivity of lines of code, it could mean something. It could mean that there's a breaking change that impacted other people. So that could be a cause for concern, not a cause for concern, cause for us to identify that something might be going on. And we might actually just get rid of that data point because it serves as a noise. Yeah.
Quick one. Do you guys use also like code quality tools or maybe the test coverage, that kind of thing?
Yeah, good question. In our case, we haven't used it before. The reason is because we don't have enough unit tests. Yeah, very embarrassing. So during the we used, although it was to be more serious though, it was an active decision not to have enough unit tests because we had to make trade-offs. So as a startup, we how should I say, we have to sprint towards liquidity. The idea is you want to quickly validate your idea before you make your app stable, because otherwise we will run out of money. So it was an active decision for us to not do it at the moment. Yeah, but good question.
You also shared the number of commits between those four projects. There is a project with thousands of commits, and then also with just hundreds. So is there why is the difference?
Yeah, why is that? So the reason is yeah, good question. The reason is because some of the products are newer. Yeah, because they're newer products, then there's less commit.